In this video, we will examine the effects of reducing steam pressure. So let's take a closer look. Now, in addition to the use of an additional heat exchanger called a superheater, as in this example, to make superheated steam, superheat can also be imparted to steam by allowing it to expand to a lower pressure as it passes through the orifice of a pressure-reducing valve, as depicted in this example. This is termed a throttling process, with the lower pressure steam having the same enthalpy as the upstream high-pressure steam. However, the temperature of the throttled steam will always be lower than that of the supply steam. The state of the throttled steam will depend upon the pressure of the supply steam, the state of the supply steam, and the pressure drop across the valve orifice. For supply steam below 30 bar gauge in the dry saturated state, any drop in pressure will produce superheated steam after throttling. The degree of superheat will depend on the amount of pressure reduction. For supply steam above 30 bar gauge in the dry saturated state, the throttled steam might be superheated, dry saturated, or even wet, depending on the amount of pressure drop. For example, dry saturated steam at 60 bar gauge would have to be reduced to roughly 10.5 bar gauge to produce dry saturated steam. Any less of a pressure drop, for example down to 20 bar gauge instead of 10.5, will produce wet steam, while any greater pressure drop, for example down to 5 bar gauge instead of 10.5, would produce superheated steam. Equally, the state of the supply steam at any pressure will influence the state of the throttled steam. For example, wet steam at a pressure of 10 bar gauge and 0.95 dryness fraction would need to be reduced to 0.135 bar gauge to produce dry saturated steam. Any less of a pressure drop, for example 5 bar gauge instead of 0.135, would produce wet steam, while any greater pressure drop, for example 0.05 instead of 0.135, would produce superheated steam. To better illustrate these important concepts, let's take a closer look at the following example. Here, wet steam with a dryness fraction of 0.95 is reduced from 6 bar gauge to 1 bar gauge using a pressure-reducing valve. Let's determine the steam conditions after the pressure-reducing valve. From the steam tables, we can see that at 6 bar gauge, the enthalpy of saturated water is 697 kilojoule per kilogram. The enthalpy of evaporation is 2066. At the exit of the valve, so at 1 bar gauge, the enthalpy of saturated water is 506 kilojoule per kilogram, and the enthalpy of evaporation is 2200. Therefore, the actual total enthalpy at 6 bar gauge at the valve inlet equals the following. So, the enthalpy of saturated water plus the enthalpy of evaporation times the dryness fraction. Now, keep in mind this quantity of heat energy is retained by the steam as the pressure is reduced to 1 bar gauge. since throttling is an isoenthalpic process. In other words, the lower pressure steam will have the same enthalpy as the upstream high pressure steam. However, the total enthalpy of dry saturated steam at 1 bar gauge equals the following. So, the enthalpy of saturated water plus the enthalpy of evaporation. As the actual enthalpy of the steam at 1 bar gauge is less than the enthalpy of dry saturated steam at the same pressure, then the steam is not superheated and still retains a proportion of moisture in its content. Therefore, at 1 bar gauge, so at the valve outlet, the total enthalpy can be expressed as follows. So, the enthalpy of saturated water plus the enthalpy of evaporation times the dryness fraction at the steam exiting the valve. Substituting for H sub F2 and H sub Fg2, we have the following. Thus, X2, the dryness fraction at the valve outlet, is 0.978. This means that the steam is still wet at the valve outlet following the pressure reduction. Okay, now in this second example, we will demonstrate how superheat can be created by a control valve. Here, steam with a dryness fraction of 0.98 is reduced from 10 bar gauge down to 1 bar gauge using a pressure reducing valve. From the steam tables, at 10 bar gauge, so at the pressure inlet of the valve, the enthalpy of saturated water is 781 kJ per kilogram. The enthalpy of evaporation is 2000 kJ per kilogram. Therefore, the actual total enthalpy at the valve inlet is as follows. The enthalpy of evaporation times the dryness fraction plus the enthalpy of saturated water. Now, to determine the degree of superheat after the valve, we will proceed as in the previous example. Recall, this quantity of heat energy, 2741 kJ per kilogram, will be retained by the steam as the pressure is reduced to 1 bar gauge. Recall, throttling is an isoenthalpic process. The lower pressure steam will have the same enthalpy as the upstream high pressure steam. The specific enthalpy of dry saturated steam at 1 bar gauge, so at the valve outlet, is as follows. Note here that the actual total enthalpy of the steam is greater than the total enthalpy of dry saturated steam at the valve outlet. This means that at the valve outlet, the steam is therefore not only 100% dry, but also has some degree of superheat. The excess energy is 2741 minus 2707. This excess energy of 34 kJ per kilogram is used to raise the temperature of steam from the saturation temperature of 120 degrees Celsius at 1 bar gauge to 136 degrees Celsius. This corresponds to 16 degrees Celsius of superheat. Now, how did we calculate the final temperature of 136 degrees Celsius? The degree of superheat can be determined either by using the superheated steam tables or by using a Mollier chart. In this video, the superheated steam tables will be used. The Mollier chart will be explained in the next video. Okay, shown now on screen an extract from the superheated steam tables. Let's shift our attention to properties at 1 bar gauge pressure. Notice that at 1 bar gauge, the saturation temperature of steam is 120 degrees Celsius. Now, since we're mainly interested in enthalpy values, let's ignore the other data. At the valve outlet and following the pressure reduction, we have determined that steam is superheated and has an enthalpy of 2741 kilojoule per kilogram. Comparing this with the enthalpy values from the superheated steam table, we can see that in our case, the superheated steam must have a temperature just below 150 degrees Celsius. Now, it is important to note here that each 50-degree temperature increment brings about 100 kilojoule per kilogram increment in enthalpy values, as shown now on screen. This corresponds roughly to 2 kilojoule per kilogram per degree Celsius. We can actually use this relationship to back calculate the temperature of the superheated steam at the valve outlet. We know its enthalpy, 2741, and we know the enthalpy of superheated steam at 150 degrees Celsius and at the same pressure, 2769 kilojoule per kilogram. The delta is 28 kilojoule per kilogram. Using the 2 kilojoule per kilogram per degree Celsius relationship, we can see that a delta enthalpy of 28 kilojoule per kilogram corresponds to a temperature difference of 14 degrees Celsius. Therefore, the temperature of superheated steam at the valve outlet equals 150 minus 14. This gives 136 degrees Celsius. Now, since saturated steam at the same pressure has a temperature of 120 degrees Celsius, then we can deduce that the superheated steam at the valve outlet has 16 degrees of superheat. This is how the degree of superheat can be determined using the superheated steam tables. In the next video, the Mollier chart will be explained, and we will demonstrate how to use this valuable chart to determine the degree of superheat.